All right, welcome back to another video. Looks like I'm in the red. Hopefully, it's not too bad. So we're gonna keep on with uh, this book. So the next section is ranking models with comparative evaluation. Often you evaluate models not because you care about their scores, but because you want to know which model is best for you. What you want is a ranking of these models. You can rank models using either point-wise evaluation or comparative evaluation. With point-wise evaluation, you evaluate each model independently, then rank them by their scores. For example, if you want to find out which dancer is the best, you evaluate each dancer individually, give them a score, then pick the dancer with the highest score. With comparative evaluation, you evaluate models against each other and compute a ranking from comparison results. For the same dancing contest, you can ask all candidates to dance side by side and ask the judges which candidate's dancing they like the most, and pick the dancer preferred by most judges. For responses whose quality is subjective, comparative evaluation is typically easier to do than pointwise evaluation. For example, and remember the difference. So pointwise is putting models side by side. So it's like a dancing contest where candidates dance, and then the judges pick which one they like the most. Point-wise evaluation is okay. So you can think of point-wise evaluation like a figure skating competition, where each skater goes one after the next, and then they're assigned points for their routine. Whereas you can think of comparative evaluation as like a uh, uh, like almost like two tennis players playing against each other. So they go at the same time, and whoever scores the point, the most points is the tennis player who wins. So. And you can do it. You can think of it like a rap battle or a dance off or something like that. But I think I hopefully it's clear. So for responses whose quality is subjective, comparative evaluation is typically easier to do than pointwise evaluation. For example, it's easier to tell which song of the two songs is better than to give each song a concrete score. In AI, comparative evaluation was first used in 2021 by Anthropic to rank different models. It also powers the popular LMSYS Chatbot Arena leaderboard that ranks models using scores computed from pairwise model comparisons from the community. Many model providers use comparative evaluation to evaluate their models in production. Figure 3-10 shows an example of ChatGPT asking its users to compare two outputs side by side. These outputs could be generated by different models or by the same model with different sampling variables. All right, so here's figure 3-10. ChatGPT occasionally asks users to compare two outputs side by side. Yeah, I remember it used to do that quite a bit. I feel like it doesn't do that quite as often anymore. But we can see if you ask it write code to write this dictionary into JSON, it'll give you two responses and have you make a comparison or have you be the judge. So this would be an example of comparative evaluation rather than bitwise. For each request, two or more models are selected to respond. An evaluator, which can be human or AI, picks the winner. Many developers allow for ties to avoid a winner being picked at random when drafts are equally bad or good. A very important thing to keep in mind is that not all questions should be answered by preference. Many questions should be answered by correctness instead. Imagine a model, imagine asking the model, is there a link between cell phone radiation and brain tumors? And the model presents two options, yes or no, for you to choose from. Preference-based voting can lead to wrong signals that, if used to train your model, can result in misaligned behaviors. Asking users to pick can also cause user frustration. Imagine asking the model a math question because you don't know the answer, and the model gives you two different answers and asks you to pick the one you prefer. If you had known the right answer, you wouldn't have asked the model in the first place. When collecting comparative feedback from users, one challenge is to determine what questions can be determined by preference voting and what shouldn't be. Preference-based voting only works if the voters are knowledgeable in the subject. This approach generally works in applications where AI serves as an intern or assistant, helping users speed up tasks they know how to do, not where users ask AI to perform tasks they themselves don't know how to do. Comparative evaluation shouldn't be confused with A/B testing. In A/B testing, a user sees the output from one candidate model at a time. In comparative evaluation, a user sees outputs from multiple models at the same time. So that's a good point. So what A/B so yeah, each comparison is called a match. This process results in a series of comparisons as shown in table 3-5. So 3-5 shows examples of a history of pairwise model comparisons. So model 1, model 2, number 1, model 3, model 10, and so on. Now, this is a good distinction that this is not A/B testing, because what A/B testing does is it says, okay, I have a user base of 1,000 people. I want to know, does this advertisement for chocolatey chocolate get them to buy the chocolate, or is this advertisement better? Is it more effective for getting them to buy chocolate than this other one? So what you do in A/B testing is you show 500 people, half of your audience, the first advertisement for chocolate. Then you show the other half, the second one, and whichever one does better, let's say that the second one does better than the first one. Now, once that's determined that it's doing better, you show that to that first group of 500 that only saw the first one, and that's the one you use going forward. So from a user standpoint, you would only see one ad. You would see either the chocolate ad number one or the chocolate ad number two, and then over time you would see that get yanked out from under your eyes and replaced with the more effective one. And then going forward, you would see the more effective one. So that's quite a bit different than what we're seeing here. Here they're showing you both ads at the same time, and they're asking for your opinion. Which one do you like better, the first one or the second one? They're not showing you an ad; they're showing you a output. But that's a good. I'm glad the author said that because I looked at this and I thought, oh, this is an example of A/B testing. But when you really dive into the weeds, no, it's not at all an example of A/B testing. A/B testing is completely different. You wouldn't see the two responses side by side like that. That would be kept hidden from the user and it would only be available to the person doing the A/B testing. What this is an example of is comparative evaluation, not A/B testing. The probability that model A is preferred over model B is the win rate of A over B. We can compute this win rate by looking at all matches between A and B and calculating the percentage in which A wins. If there are only two models, ranking them is straightforward. The model that wins more often ranks higher. The more models there are, the more challenging ranking becomes. Let's say that we have 5 models with the empirical win rates between model pairs as shown in table 3-6, it's not obvious from looking at the data how these 5 models should be ranked. So here's table 3-6. We've got 5 models. So example win rates of 5 models. A uh, right chevron B column denotes the event that A is preferred to B. So we've got model A. So this is in the testing. So model A can be chosen. Any of the 5 models can be chosen for model A. Model B, any of the five models could be chosen. And then what we're going to do is see which model wins out. So, and it could be, so we can see Model A, when Model 1 was chosen as Model A, it was significantly better than Model 2 when it was chosen as Model B. 90% of the time, of those 1,000 times, it was better. But it's interesting because, oh, okay, cool. So they never show the opposite. See, I was wondering if they would show Model 2 as Model A and then Model 1 as Model B, but I don't see that. So we can see clearly. So Model 1 really destroys Model 2, but it doesn't do so hot against the other models, especially models 4 and 5. It really does not do that well against those at all. And even Model 3, it went from beating it 9 out of 10 times to not even having a win percentage of over 50%. So we can see, it's almost like a rock, paper, scissors sort of thing where um, they each model has clear strengths and weaknesses. Given comparative signals, a rating algorithm is then used to compute a ranking uh, compute a ranking of models. Typically, this algorithm first computes a score for each model from the comparative signals and then ranks models by their scores. Comparative evaluation is new in AI, but has been around for almost a century in other industries. It's especially popular in sports and video games. Many rating algorithms developed for those other domains can be adapted to evaluating AI models such as Elo, Bradley, Terry, and TrueSkill. LMSYS chatbot arena originally used ELO to compute models ranking, but later switched to the Bradley-Terry algorithm because they found ELO sensitive to the order of evaluations and prompts. A ranking is correct if, for any model pair, the higher ranked model is more likely to win in a match against the lower ranked model. If Model A ranks higher than Model B, users should prefer Model A to Model B more than half the time. Through this lens, model ranking is a predictive problem. We compute a ranking from historical match outcomes and use it to predict future match outcomes. Different ranking algorithms can produce different rankings, and there's no ground truth for what the correct ranking is. The quality of a ranking is determined by how good it is in predicting future match outcomes. My analysis of Chatbot Arena's ranking shows that the produced ranking is good, at least for model pairs with sufficient matches. See this book's GitHub repo for the analysis. And that's okay, I'm not going to look at the analysis. Well, you know what? Let me just look at the repo though, because oops, and it looks like I accidentally highlighted, so I'll hit the X there, and then I'll click on this again. There we go. Just so that I can get to the repo. Um, yeah, and I guess it looks like what's popping up to me right now is we got some prompt examples, which could be pretty helpful. All right. So challenges of comparative evaluation. With point-wise evaluation, the heavy lifting part of the process is in designing the benchmark and metrics to gather the right signals. Computing scores to rank models is easy. With comparative evaluation, both signal gathering and model ranking are challenging. This section goes over the three common challenges of comparative evaluation. Number one, the first common challenge of comparative evaluation is scalability bottlenecks. Comparative evaluation is data intensive. The number of model pairs to compare grows quadratically with the number of models. In January 2024, LIMSYS evaluated 57 models using 244,000 comparisons. Even though this sounds like a lot of comparisons, this averages only 153 comparisons per model pair. 57 models correspond to 100, or sorry, to 1,000, almost 1,600, so 1,596 model pairs. This is a small number considering the wide range of tasks we want a foundation to do. And so fortunately, we don't always need direct comparisons between two models to determine which one is better. Ranking algorithms typically assume transitivity. If, yeah, so if model A ranks higher than B, B ranks higher than C. Then with transitivity, you can infer that A ranks higher than C. This means that if the algorithm is certain that A is better than C and B is better than C, it doesn't need to compare A against C to know that A is better. However, it's unclear if this transitivity assumption holds for AI models. Um, yeah, and that's pretty intuitive, right? It's like A is grading a paper, Model A grades a paper. It does a better job of doing that than Model B. Model B grades the paper and does a better job of grading it than Model C. But, we still need to test A against C. It's not fair to assume that just because A did better than B and B did better than C, that C cannot do better than A in this regard. There's just too many, like it's more sophisticated than that. Many papers that analyze ELO for AI evaluation cite transitivity assumption as a limitation. Yeah, so it's not the same as like a shape, because we can say like a basketball is larger than a softball, which is larger than a um, ping pong ball. Therefore, we know that a basketball is larger than a ping pong ball, but it's not the same sort of comparison. It's not like a comparison of size. It's a comparison of like capability. So like you can't just assume that the like here's a good example. Um, like 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 we can say LeBron James is a better basketball player than uh, Kareem Abdul-Jabbar because he beat Kareem Abdul-Jabbar's scoring record. But and Kareem Abdul-Jabbar is a better basketball player than Michael Jordan because Michael Jordan never had this all-time scoring record, and Kareem Abdul-Jabbar is. You can't say therefore LeBron James is better than Michael Jordan, right? Because there's other metrics to consider, like how many championships they have, how much of an impact they had on popularizing the sport, and sorts of things like that. So hopefully that makes that clear. They argued that human preference is not necessarily transitive. In addition, non-transitivity can happen because different model pairs are evaluated by different evaluators and on different prompts. Yeah, so transitivity goes out the window the moment you have um, uh, preference involved because if you're just grading on whether or not people prefer one thing over the other, it's not going to be a given case that you would prefer um, something just because uh, it was less preferred than something else. It's like just because you like a um, sports car more than you like a van, and just because you like a van more than you like a motorcycle doesn't necessarily mean that you would like a motorcycle more than you would like a sports car. In addition, non-transitivity can happen because different model pairs are evaluated by different evaluators and on different prompts. There's also the challenge of evaluating new models. With independent evaluation, only the new model needs to be evaluated. With comparative evaluation, the new model has to be evaluated against existing models, which can change the ranking of existing models. And then if you're using AI as a judge, and you're using a judge that's the same model as one of the models you're comparing, it's going to have a bias to favor the model that is more like the judging model. It also makes it hard to evaluate private models. Imagine you've built a model for your company using internal data. You want to compare this model with public models to decide whether it would be more beneficial to use a public one. If you want to use comparative evaluation for your model, you'll likely have to collect your own comparative signals and create your own leaderboard or pay one of those public leaderboards to run private evaluation for you. The scaling bottleneck can be mitigated with better matching algorithms. So far, we've assumed that models are selected randomly for each match, so all model pairs appear in approximately the same number of matches. However, not all model pairs need to be equally compared. Once we're confident about the outcome of a model pair, we can stop matching them against each other. An efficient matching algorithm should sample matches that reduce the most uncertainty in the overall ranking. All right, so then the second common challenge of comparative evaluation is lack of standardization and quality control. One way to collect comparative signals is to crowdsource comparisons to the community the way Limsys Chatbot Arena does. Anyone can go to the website, enter a prompt, get back two responses from two autonomous models, and vote for the better one. So I'm going to do control click here to open that and try that. Only after voting is done are the model names revealed. So let's do that with DeepSeek if we can. So users of the website agree to the following terms, uh, not to misuse it for. So this is meant to be used for research. Okay, so let's give a really interesting. So let's do this. So we're gonna pick which model is model A and which model. Oh, you know what? It doesn't tell you. Like that's the point, right? Like it's not gonna tell you which is better until one is selected. So let's go into uh, let's do here we go. So this is a prompt I found on Reddit, which really like puts all of prompt engineering into a neat tutorial. So we're going to expand to see. Okay, so here's the different models that might get tested. Okay, so where do oh so here's where I enter my prompt. So I'm going to use this prompt that I found on a Reddit post this morning that has all of the best, latest and greatest prompting techniques. So I think this came from r slash prompt engineering. It came from the user Kai Thought Architect, and which uh, Architects Lab. Okay, so yeah, these are all of the essential foundation techniques everyone should know when it comes to AI prompting. So so you need to be more so like if you just write like write a story, you're not going to get a very good response. Modern prompt engineering is about creating structured, context-rich instructions that consistently produce high-quality outputs. Um, so uh, so you need uh, so you can't just give it basic instructions to write something, to do this, to that. You have to give it a role to play. So you want it to do it as, a CCIE with 10 years of experience, or with 30 years of experience. You want to give it the context, the task specification, the output format, and the quality parameters. Um, the so you have to give it kind of attributes for it to act from. You have to give it an identity, basically. The second key pillar of prompt engineering is role-based prompting. One of the most powerful techniques is role-based prompting. Instead of just requesting information, you define a specific role for the AI. So once you've given it an identity, the next step to advanced prompt is to give it a role. So so you could say, okay, you're a CCIE with 30 years of experience. Write a technical analysis of cloud computing. Well, you give it an identity, but you haven't given it a role. So a role would be as a senior cloud architecture consultant with 15 years of experience. So like you're a CCIE with 30 years of experience, and now acting in your role as a senior cloud architecture consultant with 15 years of experience in this particular role. Um, uh, Analyze the current state of cloud computing, focus on enterprise architecture implications, highlight emerging trends and their impact, present your analysis in a professional report format, and include specific examples from major cloud providers. So after you've given an identity, the other key to advanced prompting is to give it a role. Then the next key, according to this post, and this is just a post from a random user. I'm just kind of taking their word for it. We'll probably get to a section on prompt engineering in this book pretty soon, but this post looks pretty good. So the next one is context layering. So use multiple layers of context to enhance output quality. So an example of layering. Yeah, so you just explicitly spell it. So you give an identity, you give it a role, and then you give it the context. So then the fourth one is um, output control through format specification. So you give it an identity, a role, the context, and then you give it the format you want it to provide to use in providing its response. Now here's the one we've all heard about, hopefully by now, few shot prompting. You give it a few practical examples. So uh, now it's missing the role. It's missing, yeah. So here, this is kind of oh, sorry, no, this is an example of this user's yeah. So I don't know how good this is. Uh, so I guess he's going to make more posts. This is just the first out of 10 posts that he plans to make. But uh, this is the example that I'm using here in this chatbot arena. So let's hit that and see what we get. Okay, so now we've got Model A and Model B. We can see they're chugging along. It looks like Model A has quite a bit more output than Model B. It also seems to be going a little bit faster. Um, so I'm not sure which will end up with more output than the other. But we've got a very long report from both of them, likely. Oh, it looks like we've got a risk matrix. That's cool. I like that. We've got a timeline visualization, which is pretty cool. Budget breakdown. Wow, that's really awesome. Um, oh, we got the same thing here. Risk matrix. Uh, we've got a timeline visualization. Uh, I like how it tried to do it with. Oh, I like this one better because it actually wrote it out. It actually tried to draw it. So, I mean, that right there. I'm gonna go with A is better. Ah, shoot. So this is okay. Well, they don't tell you which is which. Yeah, so it could be any one of those models. This is just for research only. Yeah. So at no point do you know which is which. Well, that's too bad. All right. So anyone can go to that website, enter a prompt, and get back two responses from two anonymous models and vote for the better one. Only after voting is done are the model names revealed. So this is an example of compare-wise evaluation. I selected model A without knowing which was which. Ah, look at this. So, okay, so it's they're revealed now. So this was Goblin. I don't know what that is. Goblin AI. Let's see what that is. So Goblin Tools, Goblin.tools. Yeah, so this is an AI, free AI to use with a spicy index, it looks like. And then O1 Mini are all familiar with that. That's one of the famous ones out there right now. So this is an important thing to note is like we're in a golden age of AI. There's 89 models that it's pulling from. So if you've never heard of this Goblin, this is the age we live in. Like I'm sure of these 89 models, like they're including a small percentage of the models out there. Like that there's far more than 89 models that they could evaluate. I'm pretty like I wonder if they even have UAI.com on here. And it looks like they don't have all 89 listed out. So they have one, two, three, four, five, six, seven, eight. Eight times three. They have 24. So you can't even see all the 89 models. Um, cool. I like that response. Let's do it in O1 Pro. I've actually already done it in O1 Pro. Oh yeah, here's where I did it in O1 Pro. Oh, here's the timeline visualization. I like how it tried to write it out in the other one. All right, anyway, so O1 Mini won the day on that one. The benefit of this approach is that it captures a wide range of signals and is relatively difficult to gain. However, the downside is that it's hard to enforce standardization and quality control. First, anyone with internet access can use any prompt to evaluate these models, and there's no standard on what should constitute a better response. It might be a lot to expect volunteers to fact check the responses, so they might unknowingly prefer responses that sound better but are factually incorrect. Some people might prefer polite and moderate responses, while others might prefer responses without a filter. This is both good and bad. It is because it helps capture human preference in the wild. It's bad because human preference in the wild might not be appropriate for all use cases. For example, if a user asks a model to tell an inappropriate joke and the model refuses, the user might downvote it. However, as an application developer, you might prefer that the model refuses. Some users might even maliciously pick the toxic responses as the preferred ones, polluting the ranking. Second, crowdsourcing comparisons require users to evaluate models outside of their working environments. Without real world grounding, test prompts might not reflect how these models are being used in the real world. People might just use the first prompts that come to mind and are unlikely to use sophisticated prompting techniques. Among 33,000 prompts published by Limses Chatbot Arena in 2023, 180 of them are hello and hi, which account for 55% of the data. And this doesn't yet account for variations like hello with an exclamation point, hello with a period, hola, hey, and so on. There are many brain teasers. The question X has three sisters, each has a brother. How many brothers does X have was asked 44 times. Simple prompts are easy to respond to, making it hard to differentiate models' performance. Evaluating models using too many simple prompts can pollute the ranking. If a public leaderboard doesn't support sophisticated context construction, such as augmenting the context with relevant documents retrieved from your internal databases, its ranking won't reflect how well a model might work for you for your RAG system. The ability to generate good responses is different from the ability to retrieve the most relevant documents. One potential way to enforce standardization is to limit users to a set of predetermined prompts. However, this might impact the leaderboard's ability to capture diverse use cases. Limsys instead lets users use any prompts, but then filter out hard prompts using their internal model and rank models using only these hard prompts. Another way is to use only evaluators that we can trust. We can train evaluators on the criteria to compare two responses or train them to use practical prompts and sophisticated prompting techniques. This is the approach that Scale uses with their private comparative leaderboard. The downside of this approach is that it's expensive and can severely reduce the number of comparisons we can get. So this looks like I've definitely shown before on this channel the Hugging Face leaderboard. So this is the OpenLLM leaderboard. Uh, it looks like there's another one. So O1 is in the lead. That's the one I use, O1 Pro. Huh, interesting. All right, well, moving on. The downside, yeah. So another option is to incorporate comparative evaluation into your products and let users evaluate models during their workflows. For example, for the code generation task, you can suggest users two code snippets inside the user's code editor and let them pick the better one. Many chat applications are already doing this. However, as mentioned previously, the user might not know which code snippet is better since they're not the expert. On top of that, users might not read both options and just randomly click on one. This can introduce a lot of noise to the results. However, the signals from the small percentage of users who vote correctly can sometimes be sufficient to help determine which model is better. Some teams prefer AI to human evaluators. AI might not be as good as trained human experts, but it might be more reliable than random internet users. From comparative performance to absolute performance. For many applications, we don't necessarily need the best possible models. We need a model that is good enough. Comparative evaluation tells us which model is better. It doesn't tell us how good a model is or whether this model is good enough for our use case. Yeah, and you can you can think like it also doesn't tell you like let's say you have um, hardware that can only run a model, if it just tells you which model is better than the other, you can't do something like say I need a model that has a performance level out of 10 of 6, um, and and that's because my hardware only supports a performance level of 6. It can't do sevens, eight, nine, or tens. So I need to know which uh, models have this performance level. I don't need to know which one is better than another one. It doesn't. It's not relevant to me that there's a better model. because my hardware can't run this model. What matters to me is knowing what the best model is that performs at the level my hardware can support. So you need a um, uh, criteria-wise evaluation, I think is what it was called. Point-wise evaluation is the term. All right. So for many applications, we don't necessarily need the best possible models. We need a model that is good enough. Comparative evaluation tells us which model is better. It doesn't tell us how good a model is or whether this model is good enough for our use case, as does point-wise evaluation. Let's say so the other big limitation of comparative evaluation is I think we went through the three ones already. Oh, wait, no. Well, the first one was scalability bottlenecks. The second one was lack of standardization quality control. So now we're reading about the third one. From comparative performance to, so we can't get absolute performance. That's another problem with comparative evaluation. It doesn't tell us how good a model is or whether the model is good enough for our use case. Let's say we obtained the ranking that Model B is better than Model A. Any of the following scenarios could be valid. Model B is good, but Model A is bad. Both Model A and Model B are bad. Both Model A and Model B are good. And Model A is better, but it doesn't we can't use Model A, so it doesn't matter that it's better. Model B is what we need, even though our evaluation says that it might not be, even though our evaluation recommends Model A. You need other forms of evaluation to determine which scenario is true. Imagine that we're using Model A for customer support, and Model A can resolve 70% of all the tickets. Consider Model B, which wins against Model A 51% of the time. It's unclear how this 51% win rate will be converted to the number of requests Model B can resolve. Several people have told me that in their experience, a 1% change in the win rate can induce a huge performance boost in some applications, but just a minimal boost in other applications. When deciding to swap out A for B, human preference isn't everything. We also care about other factors like cost. Not knowing what performance boost to expect makes it hard to do the cost benefit analysis. If Model B costs twice as much as A, comparative evaluation isn't sufficient to help us determine if the performance boost from B will be worth the added cost. Future of comparative evaluation. Given so many limitations of comparative evaluation, you might wonder if there's a future to it. There are many benefits to comparative evaluation. First, as discussed in post-training, people have found that it's easier to compare two outputs than to give each output a concrete score. As models become stronger, surpassing human performance, it might become impossible for human evaluators to give model responses concrete scores. However, human evaluators might still be able to detect the difference, and comparative evaluation might remain the only option. For example, the Llama 2 paper shared that when the model ventures into the kind of writing ability beyond the ability of the best human annotators, humans can still provide valuable feedback when comparing the two answers. And that makes sense if you're thinking about it. It's like, um, yeah, like even though it can operate at better than human performance, it can still be evaluated by humans uh, that can't operate at such a high level. Like, this is movie critics can still give valuable results, even if they're not like famous directors themselves. Second, can give valuable opinions about movies without having to be equal or better of a filmmaker as the filmmakers who made the films they're evaluating. Second, comparative evaluation aims to capture the quality we care about, human preference. It reduces the pressure to have to constantly create more benchmarks to catch up with AI's ever expanding capabilities. Unlike benchmarks that become useless when model performance achieves perfect scores, comparative evaluations will never get saturated as long as newer, stronger models are introduced. Comparative evaluation is relatively hard to game as there's no easy way to cheat, like training your model on reference data. For this reason, many trust the results of public comparative leaderboards more than any other public leaderboards. Comparative evaluation can give us discriminating signals about models that can't be obtained otherwise. For offline evaluation, it can be a great addition to evaluation benchmarks. For online evaluation, it can be complementary to A/B testing. Summary: the stronger AI models become, the higher the potential for catastrophic failures, which makes evaluation even more important. At the same time, evaluating open ended, powerful models is challenging. These challenges make many teams turn toward human evaluation. Having humans in the loop for sanity checks is always helpful, and in many cases, human evaluation is essential. However, this chapter focused on different approaches to automatic evaluation. This chapter starts with a discussion on why foundation models are harder to evaluate than traditional machine learning models. While many new evaluation techniques are being developed, investments in evaluation still lag behind investments in model and application development. Since many foundation models have a language model component, we zoomed into language modeling metrics, including perplexity and cross entropy. Many people I've talked to find these metrics confusing, so I included a section on how to interpret these metrics and leverage them in evaluation and data processing. This chapter then shifted to focus on the different approaches to evaluate open-ended responses, including functional correctness, similarity scores, and AI as a judge. The first two evaluation approaches are exact, while AI as a judge evaluation is subjective. Unlike exact evaluation, subjective metrics are highly dependent on the judge. Their scores need to be interpreted in the context of what judges are being used. Scores aimed to measure the same quality by different AI judges might not be comparable. AI judges, like all AI applications, should be iterated upon, meaning their judgments change. This makes them unreliable as benchmarks to track an application's changes over time. While promising, AI judges should be supplemented with exact evaluation, human evaluation, or both. When evaluating models, you can evaluate each model independently and then rank them by their scores. Alternatively, you can rank them using comparative signals. Which of the two models is better? Comparative evaluation is common in sports, especially chess, and is gaining traction in AI evaluation. Both comparative evaluation and the post-training alignment process need preference signals, which are expensive to collect. This motivated the development of preference models, specialized AI judges that predict which response users prefer. While language modeling metrics and hand-designed similarity measurements have existed for some time, AI as a judge and comparative evaluation have only gained adoption with the emergence of foundation models. Many teams are figuring out how to incorporate them into their evaluation pipelines. Figuring out how to build a reliable evaluation pipeline to evaluate open-ended applications is the topic of the next chapter. So, oh, right. So, really moving through this fast. We're already on chapter 4. 30% of the book, nearly a third of the way done, of a thick, thick book. So this is good. And I'll just skim these footnotes. Anything that looks interesting links or something I'll look at briefly, but I don't want to get this series is already going to take forever to get through, so I don't want to spend too much time on this. This will be the end of this chapter. Next video will be the start of chapter 4. So here we go. Terry Tao, one of the best living mathematicians that we know of in the West. I'm sure there's mathematicians that nobody's heard of in the West that are quite good at math. But Terry Tao is let's look at let's dive into the Terrence Tao rabbit hole a little bit because this man, like, my God. Um, I think he got, let's see what age he was when he got his PhD. So he's 49 years old. He was born in 1975. Um, and there we go. So he attended, he started going to university at the age of 9 to study mathematics courses. Um, he is one of only 3 children in the history of Johns Hopkins Study of Exceptional Talent program to have achieved a score of 700 or greater on the SAT math section while just 8 years old. He scored a 750 on the SAT when he was 8. Um, he was the youngest participant in the International Mathematical Olympiad. He first competed at the age of 10. Um, and when he was 11, because he was born in 75, he won a bronze. The very next year, when he was 12, he won a silver, and he got the gold medal in the International Olympiad competition at the age of 13. He remains the youngest winner of any of those medals ever. So no other 10-year-old got a bronze, no other 11-year-old got a silver, and no other 13-year-old got a gold. All right, um, so in 1991, um, he was 16 and he got a bachelor's and a master's degree from Flinders University. In 1992, the very next year when he was 17, he got a Fulbright scholarship um, um, at Princeton. Um, and then he became a graduate student. Then he got a PhD at the age of 21, which is pretty good. Like, I mean, a PhD is a PhD. Like, he's not going to get a PhD at the age of like 15, right? But like, I think what's the average age people get there first? We're gonna. What's the average age that people get their first PhD for the people who do? Yeah, in the US it's like 32. Like it takes a long time to get a PhD because you have to get the bachelor's first, you have to get the master's. So like, we're talking about we're talking about it takes 4 years just to get a bachelor's. And even before that, to graduate high school, all that. So he got a PhD at the age of 21, which might, if you're not familiar with like what it takes to PhD, it might sound like he's not that young getting it, but we're talking about PhD here. Like most people are in their mid 30s when they get their first PhD. And he became a full, and if as if that wasn't uh, impressive enough, he became a full professor at UCLA when he was 24. He's the youngest person ever to have been a full professor at UCLA. Um, in throughout the history of that institution and still today. This was 1999, so it's been 26 years later, and he's still the youngest person ever. So he is a once in a generation mathematical mind. Um, and there's basically no one else like him. Like he's the smartest of the smartest. And the other cool thing about him is he's a collaborator. He's not just a stereotypical mathematician that sits alone in a closet writing out equations. Like he is known for his collaborations. Yeah, so I just wanted to put that out there because like it's important to know who these people are, right? Like we all know who like Elon Musk is, and we all think, oh, Elon Musk is this brilliant person. But like I think a lot of people have no idea who Terrence Tao is, especially since he doesn't even go by Terrence Tao. Like he goes by Terry. Like his name is Terry. He like his blog is Terry Tao. So like the name that's out there for him isn't even the name he goes by. His name is Terry Tao. His first name is Terry. So like, he I think most people have never heard of this before, and like, this should be your baseline for like who is the smartest person in the world. Like they have to be as smart or smarter in terms of life accomplishments as Terry Tao. So didn't even Elon Musk is the wealthiest man in the world, but Elon Musk doesn't even have a um, this is not what Elon Musk's blog would look like. I doubt there would be equations on it, which is sad because he bills himself as a genius engineer that knows more about engineering than anyone else. And in the meantime, somebody like Terry Tao isn't like when's the last time there was a speech by Terry Tao? Like there should be. And he's a great collaborator too. Like I feel like he could give a speech and like it would make sense. Yeah, and see, like the first thing on his blog is just this simple flattening the curve, mathematical concept. Like that's the other, I think, kind of misconception about mathematicians is they're just like, they're focusing on like how do I uh, turn a sphere inside out, assuming that the sphere has magical properties where it can pass through itself, but yet it doesn't have a magical property that it can't rip or tear. It's like mathematicians like Terry Tao aren't just off in the weeds, clouds, thinking about stuff that doesn't matter. Like the thing front and foremost on his blog is how do we present the healthcare system from being overwhelmed by people being infected by the pandemic? That's a very important question. That's not like turning a sphere inside out. So I think the idea that mathematicians are off in the weeds working on abstract things that nobody cares about is, uh, at least in the case of Terry Tao, not true. All right. So huge fan of Terry Tao. I wish I could read his blog, but new exponent pairs, zero density estimates, and zero additive energy estimates, a systematic approach. Yeah, I'm not sure, not sure how far I would get on this. Oh, Andrew Yang? Like who? Like this must. Yeah, this is a mathematician. Oh, okay. All right, moving on. So that's Terry Tao. So he compared the experience of working with this model to working with a mediocre but not completely incompetent graduate student. So there you go. Like for Terry Tao, that's like, take it or leave it, probably leave it. But for somebody like me, it's like, oh my God, like I'll take that. A mediocre but not completely incompetent graduate student, man, I'll talk to that thing all day. He speculated that may only take one or two further iterations until AI reaches the level of a competent graduate student. And at that point, it's like, for somebody like me, like I am going to at least 10x. In response to his assessment, many people joked that if we're already at the point where we need the brightest human minds to evaluate AI models, we'll have no one qualified to evaluate future models. And that's a good point too. Is like, this is not just anyone's opinion on how well they work as a graduate student. This is Terry Tao's opinion. So, what's his perception of a mediocre but not completely incompetent graduate student? Probably some of the best graduate students out there throughout history that there have ever been. Generational talents of graduate students. Anyone else would probably um, say that it functions much higher as a graduate student than he might. All right, so just going through this, just skimming everything, not reading it all out loud. Oh, here's something about Claude Shannon. I'm a big fan of Claude Shannon. He's a juggler, which I really like. Like me, that's his primary hobby. Um, but unlike me, he has really contributed meaningful, long-lasting work. Uh, okay, supervised fine tuning. Yeah, I remember that. Okay. That's a good point. So the term AI judge is not to be confused with the use case where AI is used as a judge in court. So a better way to call it would be a AI evaluator. It's the idea of using an AI to make determinations rather than a human. It's not the idea of interpreting and applying the law. Okay. All right, so that brings me to chapter 4. So I'll move the bookmark forward, and that's it for this video. Thanks for watching, and see you in the next one.